So, all right. Should I restart? Yes, okay. So, sorry, we had a little technical problem here. So, anyway, I want to to welcome you to this seminar that whether or not you're at home, in front of your computer, or here in the auditorium, in 210 auditorium. So it's really my pleasure to introduce our colleague, Professor Jia Liang, who joined the department in 2010. So just a few words about his academic trajectory so far, that he obtained his BS degree and MS degree from the National University of Singapore, went to work for 1 year for Atype, and then he entered the graduate program at Northwestern University in 2006 with Professor Bajan as advisor. So he graduated in 2010, joined our department at that time, and has built a very strong program in the emerging field of probabilistic mechanics of quasi-brittle structures, and also probabilistic failure analysis of quasi-brittle materials. So he has been recognized for his work by several awards, and I will cite only two of them. One is the Da Vinci Award from the Engineering Mechanics Institute that he received in 2017. And last year, he was awarded the Young Investigation Medal from the Society of Engineering Sciences. He's a prolific writer. He has probably, I think, more than 60 papers in refereed journals. He's co-author of 2 books. One is a research monograph, and the other one is in the latest, I understand, the latest form. It's a draft form, but it's going to be published by Oxford University probably next year. So I would just want to add a final note that Jia Liang has established collaboration with many of us in the department, in the college, in university in the US and abroad. So please join me from home to welcome him for today's lecture.
Okay, thank you, Emmanuel, for a nice introduction. Very good morning. It's a great pleasure to be here to deliver a oral lecture. And thank you for coming in person and joining me at home. So today, I would like to talk about our recent work on a level excursion analysis of a probabilistic quasi-brittle fracture. This work is in collaboration with my former PhD student, Zhifeng Xu. Now he is going to join faculty in Wuhan Technological University in China. So first of all, I would like to give you a brief overview of quasi-brittle structures. Quasi-brittle structures are made of quasi-brittle materials, which are brittle heterogeneous in nature. And there's a vast variety of these materials in civil engineering applications. Okay, the typical example is concrete, composites, ceramics, rock, polycrystalline silicon, and memscale, and many, many more. And these materials have been widely used in applications, ranging from mega scale civil infrastructure like dam, modern aircraft. Now we know Boeing 787, 95% of the fuselage was made of composites. Ship hull in the US Navy, the ship hull now is also composite instead of metal. And again, at a micro scale, we have microelectronic devices are made of polycrystal silicon. And I think most people will acknowledge the fact that no structures can be designed to be risk-free. So a very important challenge in design and analysis of these structures is that we have to ensure the structure will not fail at a certain risk. And that kind of risk is on the order of 1 in 1 million. And that really imposes a particular challenge in analysis and design. Because we simply cannot determine the design strength at that failure probability by direct experiments or simulations. So we are looking at, if we want to determine the design strength at a 1 in 1 million failure probability, we will need to perform trillions of experiments. So in this regard, we have to rely on modeling, okay, analytical modeling. That's the only way to do this. So if you go to the literature, 99% of literature on strength distribution will use a Weibul model, which was proposed by Weibul in 1939 in Sweden. And the model really get known to the US community is in 1951, where he published the same paper in Journal of Applied Mechanics by ASME. Because this model is so widely used, I think people get a wrong impression that this model is empirical, but actually it's not. This model has a very, very well-established theoretical background. That is extreme value statistics. So here I want to show you that the Weibul distribution basically written in this form, where we look at the probability that the peak load of the specimen is less than some value sigma is expressed by this expression. And the fundamental idea behind this is that we can treat, basically we treat the specimen as a peak load as a chain of elements linked together. And the key point here is that this number of elements, n, is going to infinity, okay? And so Weibul himself published his paper in 1939. Actually, he didn't realize that this problem was investigated before him by Fisher and Tibet in 1928. Fisher and Tibet are mathematicians at Cambridge. And of course, when they look at this problem, they have any inclination in engineering applications. They treat it as a pure mathematical problem. So the way to solve this problem or derive this equation from an infinite chain is through the concept of a stability postulate. So the idea that Fisher and Tibet had when deriving this equation is the following. They consider a chain of elements where n is equal to infinity. And what they do is that they try to group those elements, okay, in Q groups, and the Q is finite. Because n is infinite, so the number of elements in each group is infinite. Okay, and then you can write down this equation where the strength distribution of the entire chain is related to the strength distribution of in each element. Since each element is also of infinite chain, so what follows is that the strength distribution of each element and the strength distribution of the entire chain must follow the same functional form. It only differs by a linear transformation. So when we write down this equation, we will come up with the functional equation for F, where F is the strength distribution of a chain. The question is what function F can satisfy this equation? So in the classical paper by Fisher and Tibet, they propose 3 functions. And now we know it's a Gumbel distribution, Fleischer distribution, and a Weibul distribution. And the uniqueness of these 3 distributions was proven later by Gentengu in Russia, about 10 years, in 1945, in fact. But nevertheless, you can show that if, okay, that's a condition, if my fx has a power law tail, it's extremely important here, assumption. If my fx is a power law tail, then this functional equation will give us the Weibul distribution. So the bottom of Weibul distribution is that it was derived from infinite Weak-Sling model, but at the same time, the tail distribution has to be a power law. If a tail distribution is not power law, then you will not get the Weibul distribution. Okay, so how about the actual test data we have on hand? If you go to literature, there's really a vast number of tests has been performed on structures. So here I want to show some examples of a laboratory test on different quasibrittle structures. So on the left, you see is a ceramics, silicon nitride. The concrete in the middle is tested by Weibul himself. And on the right, you have a cold asphalt that the test did here at Minnesota in collaboration with Professor Stano. So you can see that I plot everything. This is the histograms, okay, of distribution function in the Weibul scale. So if the distribution follow Weibul distribution, you will see that it's a straight line. And clearly you see that none of them is straight line, which means that these distribution we measure in the laboratory scale test will not follow Weibul distribution. And why is that so? The inapplicability of a Weibul distribution to the laboratory scale test is because In those specimens, the specimen size is not that large compared to the size of a damage zone. And because of this, we cannot argue that this n is infinite. So this breaks down the key assumption of an infinite weak-slip model. And that is why that the Weibul distribution does not apply to model these specimen distributions. So to address this fundamental problem, the recent developments is that we propose a finite weak-slip model. That is my PhD work with Danik. So here we still think that the specimen is modeled as a chain, but now we relax the assumption. We say n is not infinite, n is finite. Of course, it seems to be a simple simple relaxation of the condition, but it will lead to a quite involved work if we want to determine the distribution of the chain with n is finite. But yet we did that, and the model that finite weak-slip model is able to fit all these kind of non-Weibulian tests data. The recent work at Northwestern by Danik and Lohr is on the fishnet statistics. Here they basically look at the specimen is modeled as a discrete lattice, basically. And of course, this is more complicated, and you can look at whether you can also imagine that this could capture the distribution of a damage in a stochastic way. But nevertheless, I want to point out that both finite weak-slip model or the fishnet statistics are all discrete type in nature. So if you think about the weak-slip model, we need to think about the specimen is represented by a chain of elements. Once we do that, we have to introduce the length scale. Otherwise, we don't know how large the one element is. So that is the artificial length scale we input in the model. And at the same time that we have to assume that the peak load of each element are statistically independent. So in that sense, actually, we ignore the correlation structure of the random field in the specimen. So I would say that these two models are simplified mathematical model for this purpose. So on the other hand, we know that in the literature, there's a vast amount of work looking at the flaw statistics, which of course these two models are not explicitly capture that. So here that today I want to talk about one model is more general than these models. We want to look at without introducing artificial length scale, yet we can capture the non-Weibulian statistics in the strengths of the structures. The development of the model is really motivated by the recent work on the MEMS devices. So in recent years, there's more interest in looking at the failure statistics of MEMS structures, just because those MEMS devices are widely used in some critical applications in defense. So here I showed again that what is the test results on the peak strength of the MEMS devices. So on the left, you see this is on-chip test on a MEMS dog bone test that was performed by Brad Boyce at Sandia. The specimen length is about 20 microns. So we look at different types of MEMS materials. And again, I plot on the Weibul scale. You can see clearly that there is a deviation from a straight line. So it was believed that the variability of the strength of the MEMS device arises from two sources. One source is a random surface geometry. If you really zoom into the sidewall geometry of the dog bone specimen, you see they are not smooth. They are looking like something like that. So you have a lot of grooves, and that's a natural consequence of the fabrication process. And now you can see that once you have a surface grooves, even if I apply a deterministic stress sigma 0 on a far field, the stress field inside the specimen is totally random because the geometry of the groove is random and no control of those randomness of the grooves. The second randomness comes from the material resistance. So the local material strength has a randomness as well because the strength at this point may not be the same as strength as the point next to it. So those randomness interact each other and causes the randomness we see in the overall peak load. So the question is that can we develop a model that can capture the randomness in a single framework? So that is a goal. So I want to start with the model that we developed. To determine the peak load distribution, we have to first of all try to propose a failure criteria, okay? So here we consider a uniaxial tension specimen, which is, I think, the specimen that you will use in the laboratory test on the on-chip test. But the specimen with a random sidewall geometry here. Okay, so basically we have a specimen like this with some sidewall geometry is random. And the groove that we idealized by the V notch, basically, okay? So there are 3 parameters we use to describe the randomness of a surface sidewall. One is the notch, the V notch depth, V notch angle, and the V notch spacing, okay? So these parameters are random, basically, okay? That describes how random the surface is. Okay, now we want to propose a failure criteria at material point. And so way we choose a failure criteria, we choose a non-local model where basically we average stress, okay, in x direction along the y direction first, then we do the non-local average along x direction. The reason to take a non-local averaging twofold. The first is that when we do a non-local averaging, we eliminate the infinite stress as a notch tip if we use elastic analysis. Because once you take this integral here, you eliminate the stress singularity at the tip. Second is that physically, non-local averaging actually accounts for the finite size of the fracture process zone. That allows us to describe the failure statistics in a continuous setting. And I want to point out that when we introduce the weighting function alpha, we introduce a length scale there because the non-local averaging has for example, a bell shape. So you have a decay zone and you do have a non-local averaging length scale involved. That length scale typically is on the order of, I would say, the same as the width of the process zone. So the point here that when we do non-local averaging, I do introduce a length scale here in the weighting function alpha. Okay, now we look at the specimen level. So the failure criteria we choose based on the damage localization is that the specimen will attain its peak load when at any point X along the sidewall, the non-local stress reaches the material tensile strength. Physically, is that you will have a process zone fully formed along the sidewall. The point here is that I don't know where this point is. It's any point X, but I don't know where this point is. So mathematically, what I write here is nothing but a material point failure criteria sigma bar X is non-local stress equal to FTX, where FT is the material strength. Now you can see that at this point, you can see that the randomness comes into picture. First of all, because F sigma bar X is random because the geometry of the surface groove are random. And the material strength FT is also random. Okay, so we have an interaction of 2 random fields, basically. And what we want to determine is that at which point this failure will occur. Okay, so now if we choose elastic analysis, then we can say the non-local stress sigma bar X can be normalized in terms of the far field stress I applied. So we can write sigma bar X equal to the far field stress sigma 0 times Zx. So Zx will be a dimensional stress field. It's random. Okay, so now let's denote the sigma m is a maximum stress I can apply the far field. Then the cumulative distribution function CDF of sigma m can be written as this equation. So the probability of the sigma m is less than the value of sigma n is nothing but the 1 minus the survival probability. Survival probability is that at any value x, any location x along the sidewall, I will always have my strength is bigger than the stress. Okay, so basically we write on the face survival probability. So 1 minus that will give the failure probability. Okay, so the question is how we can compute this survival probability. Okay, so since we are looking at the uniaxial tension specimen, okay, the simplest case. So what we can do is that we can decompose. First of all, we can consider that the strength field FTX and the dimensional stress field ZX as a homogeneous stochastic processes. So by doing this, we can decompose it to a mean and a 0 mean fluctuation. Okay, so mu FT is the mean value of FT and the remaining part is the fluctuations random, but it's 0 mean, of course. Okay, by using these two node decomposition, and we substitute into this equation, then you can find that I can define a new random field, eta 0x. Basically, I just combine the random field of zx and ftx together. Okay, and then we get eta 0x, which is a combined random field from the stress field and the strength field. And on the right-hand side is a lambda, is a constant, okay, for a given choosing parameter of strength. Okay, then this becomes a very simple picture here, is that what I want to calculate is that eta 0x is a random field in 1D. Okay, so I just use, for example, a random curve to represent this. Lambda for given sigma n is a constant. So what we are calculating here is nothing but what is the probability at which this random curve will never protrude this barrier lambda. And that is a classical problem in mathematics, is what we call a first passenger probability or level crossing. And that problem can be solved through level excursion analysis. So how we solve this? So we calculated basically a non-crossing probability, which means that the curve does not pass the barrier. Okay, this problem was investigated by Valmak. At the time he was at MIT. So he basically said that the probability of a non-crossing is equal to the survival probability of a starting point, which basically at a starting point by eta 0x, the curve had to be less than the barrier. And then we use a modified Poisson process to approximate the crossing process. So here the key point is that he introduced this mu lambda. Mu lambda is a mean crossing rate. So physically, this mu lambda you can think about is how fast this curve is passing the barrier. So of course, this curve is random, is random in geometry. So this mu lambda actually mathematically is expressed by the conditional expectation of the positive gradient. So we can just basically write in this way, and you can express in the integration by this. So the difficulty comes into this expression. So we do need to determine the joint probability density function of eta 0, which is a random field, and the derivative of the random field, the gradient of the random field. In most cases, the random field and the gradient of the random field are not independent. So, which means that this joint probability density function is very hard, if not impossible to evaluate. But the good news is that if my eta 0 is a Gaussian process, then you can prove that eta 0 and the gradient of eta 0 will be independent. Once it's independent, you can decompose the joint PDF as a product of the PDF of itself. So by doing this, by knowing this, what we do is that we know that eta 0 may not be a Gaussian. So what we do is we transform it to a Gaussian process first. So we, by Gregorius work, that what we can do is that we can transform eta 0 to an equivalent Gaussian process. Once we change to the Gaussian process, then this joint PDF can be decomposed, and you can get an analytical solution of that. So basically, in the end, there's a mu lambda, the crossing rate in an equivalent Gaussian process, it can be expressed in this form, where delta, this term is a standard deviation of the gradient of equivalent Gaussian process, which can be computed from a spatial density function. So the whole idea here is that we have an eta 0 field. What we do is we transform it to equivalent Gaussian field to calculate the equivalent crossing rate and use that to back calculate the crossing rate of the actual process. So I want to show that how this can be applied to the real experiments. So here is the section tester developed by Brad Boyce. So this is really a creative test apparatus that can allow us to test the strength of specimen, hundreds of specimens in one shot. So what they do here is that they have this chain. You can see there's one chain here, one chain here. This ring, basically use the AFM tip here to probe the ring to apply the load. And you can see that if I zoom into one unit here, what you see is that you have a specimen here, and then you have a rigid link, two rigid link here, okay? So you can imagine that if I apply the load to a chain, the weak element will, the weak specimen will fail first. So you can record the peak as the breaking load, Then after this specimen is breaked, after this specimen breaks, then the load is transferred by the two rigid link. Then the load is transferred to the next specimen. So you can sequentially break the specimen, and then you can record the breaking load of each specimen. Of course, this is only, we are interested in peak load only. We are not looking at post-peak, right? So it's a load control test. At the same time, Brad also investigated this sidewall geometry, and he basically proposed this kind of distribution functions for the notch angle, notch depth, and notch spacing. So we use this information. First off, we basically did elastic stochastic phenomenon analysis to look at the random stress field. So we apply far field stress, unit far field stress, and we computed the random stress field, Zx. And that what we get is this CDF of Z. Okay, so you can see Z is range from 1 to 5, essentially. And then at the same time that from the simulation, we can also compute the autocorrelation function of Z. It decays like this. So you can see that it does have a clear autocorrelation function for stress field. That autocorrelation length really is influenced by the notch geometry, you know, how close the space the notch can have. At the same time, very important is that we also introduce the numerical averaging. The numerical averaging for stress field is typically on the grain side of polysilicon is net 25 nanometer-ish. So you can see that these two length scale actually determines the correlation structure of the stress field. On the stress side, the CDF of strength, we use a Weibul Gaussian distribution, which we proposed during my PhD work. So the bottom line is that we have a Weibul tail and with a Gaussian core. Okay, it's a kind of graph distribution. At the same time, we impose a correlation function for FTX with a kind of exponential function for the correlation. Okay, so with that, so for the stress field is determined basically from the geometry of the surface groups. For strength is calibrated. We don't know what the parameter is, so we do fit by test data. So here is a comparison with the test data by Sandia. On the first row, what you see is tested by Reedy and the Brad Boyce and the Sandia. And the second row is a test by DeBoer and the Carnegie Mellon. So I want to point out here first is that in the MEMS community, the good thing is that they always do size effect tests. They never do one test with one specimen size. They always do different size specimens. And I think this is extremely important, okay? So what you see in the first row is that I have a specimen with two different gauge lengths. One is a 20 micron specimen, the next is 70 micron specimen. You can see that this model, our model can fit both at the same time with one set of parameters. If you choose other models, which we see from literature, from a Weibul model, you can fit both, but not at the same time. The parameter has to change with specimen size if you want to enforce the fitting. However, that you have no model can predict the relationship between the parameter and the specimen size. That means that you cannot do extrapolation at all. Because if I do maybe the gauge length 100 microns, you will have no idea what parameter you will choose unless you test it and fit it. So it's totally no prediction capability of the model. Our model can use a one cell parameter can fit both of them. Similarly, on the test data from Carnegie Mellon. But one thing that you can see that this data, the second row of data may not be so smooth compared to the first set because you have a far less number of tests compared to the first set of data. This data, you have I think 1,200 data points. Here you have just less than 100 data. So you can see it's more rugged. All right. So I want to really focus on the one consequence of this model is size effect. Okay, so we try to look at what kind of stress distribution of the uniaxial tangent specimen with different specimen size. So this is the equation that basically we use. Okay, so you can see L is basically the specimen size. Now, just to show you the entire picture, I calculated the specimen of the size from 100 nanometer all the way to 10 millimeter, of an enormous size range, plot the Weibull scale. Now you can see that for small specimen size, you can see the totally nonlinear behavior on the Weibull scale, which means the Weibull will not work. And we know why, because it's not infinite weak link. Now, increased specimen size, you can see that these distribution functions start to be more and more linear on this plot. Actually, in the end, actually, it will follow exactly a Weibull distribution. So you can see that there's a huge size effect on the strength distribution type from a non-Weibulian approach to Weibull distribution as specimen size increases. The second observation is that doesn't matter what kind of specimen size we are looking at, the tail distribution is always power law because it's straight line on the Weibull scale, and that gives the power law distribution. And that is why that we will get a Weibull distribution for the specimen which is very large. And more important is that you can see that the stress at which the power law tail ends is constant, does not change with the specimen size. So the point that where the power law tail terminates actually move vertically up. Okay, that is really the feature of this model. It predicts that we switch from a non-Weibull distribution to a Weibull distribution, and the termination point of a power law actually move vertically up on the scale. The stress at which the power law tail terminates is constant. Now, if I plot the mean behavior, so I calculate the mean strength by this distribution, we get a mean size effect curve. And this is the mean size effect we will see. I plot in a double log scale, okay, log sigma m mean and the log specimen length. Okay, this black curve is the calculated results. And you can see that on double log, the good thing about double log is that I can see the power law asymptotes if any available. So now you can see that on this plot, we have 3 asymptotes with power law. The first is that when the specimen size is very small, I have a vanishing size effect. So the strength is proportional to the length to power 0, so it's constant. Then in the intermediate asymptote, we have this power law with some exponent 1 over q. And they have a large asymptote. Large size asymptote is L to power 1 minus m. This m is the Weibul modulus, and we know that this is a Weibul size effect, which was proposed by Weibul himself in 1951. But I want to take some time to explain what are those those asymptotes come from. So small size limit, we see that this mean strength does not change with specimen size. And why is that so? Actually, the reason is very simple. If you can just imagine specimen is very small. If a specimen is very small, then you can see the failure statistic at each point become fully correlated. There's no, because we do have a correlation structure here, right? So if a specimen size is small, if one point fails, the next point will fail together. So therefore, the mean strength has to be a constant. Okay, that is basically why we have a constant value here. But now you can see that the first asymptote, second asymptote was intersect at the length scale LP. So can we tell what is the meaning of this LP? If we follow this autocorrelation structure, this LP is clear. Basically, LP is where my autocorrelation's length finishes. If the specimen size is larger than the autocorrelation length, of course, they are not independent. You will see the size effect. So, but on the other hand, you can see that the autocorrelation length of eta 0 depends on sigma n, where sigma n itself is random. So we can say that the LP, the length scale for the first intersect, is proportional to an averaged autocorrelation length, which compute as expectation of the autocorrelation length of eta 0, which is given by this equation. You can calculate exactly what the LP is, in fact, by this equation. And the point here, you can see that we do have autocorrelation length of eta 0 that's affected by 2 things. Okay, one is the autocorrelation length of FT, the material strength random field. At the same time, it's also affected by the numerical averaging length scale. So this LP, this LA or this LP contains the both energetic and the statistical length scale. It's not only statistics, but also energetic too. Okay, now we move to the large size asymptote. Why large size asymptote will give us a power law with a exponent -1 over m? Well, what you can think about now is that a specimen is huge, okay, in length. Now what we can see is that we can now group the potential failure sites, okay, in groups, okay. This group, I can choose any length because my specimen size is long enough. So I can choose a big group, right? What matters is we want to consider the minimum failure load of each group. If my group size is large enough, then the minimum load of each group will be independent. They will not see each other's correlation anymore. And that actually leads to the Wixing model, if you think about that. And that's why that our model is a continuum generalization of the Wixing model. In the Wixing model, we have started with a group that is independent of each other. But of course, in our model, we can really zoom into what is inside the group. So by doing this, and the tail is a power law. So by postulate of stability, we can write the Weibul distribution in this form. And if you calculate the mean value for Weibul distribution, you automatically will give this scaling L to the power 1 minus 1 over n. That is why that we recover the Weibul size effect at the large size limit, just because that we can really do this kind of regrouping in the failure sites. Okay, so what in the second length scale, LW? LW is where that I switch from intermediate asymptotic to the Weibul scale. Okay, so if you think about in the probability plot, what we have here is that on the Weibul scale, okay, this is a power law tail, okay, with some nonlinear behavior here for specimen length equal to LP. When the specimen length become LW, I will imagine that almost everything is a Weibul distribution. So because the stress at which the power law tail terminates is constant. So now we can choose, let's say that my PFW, where the Weibul part that terminates for LW is say 90%. And the PT0 is where for specimen length LP, where the power law tail terminates typically on the order of 10 to the power minus 3. So you can calculate exactly this equation that can relate my LW to LP. And the constant, the proportional constant is determined by where my power law terminates for small size specimens. So the bottom line here is that even though in the mean size effect you do see two length scale, LW and LP, but the key length scale is still LP. LW is proportional to LP. The proportional constant is depending on the tail extent of the power law. Okay, and also you can do more than that. I mean, you can approximate the size effect curve by a simple equation like this by asymptotic matching. I have to say that we are very excited about this result because this is a classical, the result we obtain is a classical, what we call energetic size, statistical size effect, has been studied for decades. To our knowledge, this is the first analytical model can predict the entire size range. Previously, we can only predict the part of it, but this model can really predict from the small size limit with zero size effect all the way to large size effect with a Weibul scaling. So I want to also mention, we talk about MEMS devices, how this curve compare with the other tests. So this is a collection of a bending test on concrete beams, okay, 3-point band or 4-point band. And here, what we do is we normalize this with some length scale so they can collapse on the same curve. And now you can see those data points are different tests in different labs. And you can see that this is exactly follow this shape. Of course, we are not going to reach the small size limit because for LP for concrete is typically 2 aggregate size. So we look at like 40 millimeter. So you can hardly imagine that you can break a beam with a depth less than 40 millimeter. So typically the beam size we use in test is more than this LP. So we are not going to reach this part. So at that time, we believe that this part, the small size limit of a size effect is not quite important for real application because we are not going to make a specimen that small. Until that this summer, we found out test data by physicists on fibers. What they did is a remarkable size effect test on fibers. They test the fiber from 1 millimeter to 1 kilometer. 10 to the power 6, 1 million size range. And then they plotted this. This data point is what they have. You can see that remarkably this matches the first part of the curve, not this part, the first part. So we think why that's so. Well, if you look at the fiber they tested, actually it's not a single fiber. What they did is really a bundle of filaments twist together and then they pull it. So what they have is really that they have a huge shear length here in the specimen. And we can see this LP is around 200 millimeter. So we did a rough calculation. If I want to review the Weibul size effect, that test, we need to go to 30 kilometer long fiber to get one. So I have to say that this size effect curve really is range from a huge scale in the size range. In experiments, I doubt that we can really get some test result can show the entire thing. So available test is that either you test this part, which is amazing to me, okay, in this test, or you test the part, the later part, because that's a limitation. Because once you have this LP here, you want to design specimen is smaller than LP and larger than LP. That's a limitation of the test specimen we can have in the lab. Okay, but we are very excited to see that at least different tests show different parts of the curve at least. All right, so in the second part of my talk, I want to switch gear. I want to focus on the power law tail distribution of the strength statistics. Why this is important? Because I think this, as I mentioned in the first slide, this is a key assumption of Weibul distribution. Without justification of a power law tail, we cannot show that the Weibul distribution can work. On the other hand, we know in the literature, if we look at test data on the fine-grained ceramics, we know Weibul distribution works. If Weibul distribution works, that means that the tail must be power law. But why must be power law? If you go back to Weibul's work, he basically make an assumption. Okay, so why must it be power law? Is there any physical justification for that? Going to literature, you will find that very few people look at this, even though everyone uses it, but no one really tried to justify why it must be power law. The first paper that I know that who did it is Frentau at Columbia. He is really the pioneer in probabilistic mechanics. What he proposed is the flaw statistics in 1968. So he considered a bulk solid with a lot of small elements. Each element, the breaking load of each element is determined by the largest flaw in the element. So he just said, okay, why not just use the fraction mechanics, LEFM? So K1 equal to a constant times sigma, the breaking stress on the element, times square root A. A is the flaw size, largest crack size. Then the sigma reached the peak load when K1 goes to K1C. Then what he introduced is really a statistic of the flaw size. So he didn't look at the resistance side. He looked at the flaw statistics. And by assuming a Fresher distribution of flaw size, and then he can recover Weibul distribution. So he claimed that if you consider a particular type of flaw size distribution, you will recover Weibul distribution. Of course, from today's viewpoint, this analysis is kind of oversimplified because you consider LEFM, that the cracks are not interacting, so on and so forth. But I think we have to look at his work in the time that he wrote it. I really admire his insight on how to combine fraction mechanics and probability. I think that is really something at that time is really new, because 1968 is where LEFM just started to be popular. At that time, he really had a venture to combine these two things to explain a fundamental problem. I think for that really is a pioneering idea. Okay, so on the other hand, I have to point out that this is not a complete justification because you have to assume a flaw size distribution. If I change the flaw size distribution, you will not get Weibul back. Okay, so it's an assumption to another assumption. All right, so what we did is that on the other hand, that we also look at the material strength side, okay, instead of a flaw statistics, what we did is that we look at a nanoscale crack, okay, propagates through a nanoscale by breaking those bonds. And at the nanoscales, the crack propagates in a thermal activated motion. The frequency of the bond break can be described by a Kramer's equation. And then the motion of the crack propagation can be explained by a one-dimensional random walk. And then you can calculate the occupational probability of the crack tip. And that will lead to a Fokker-Plonk equation. But it's in a general sense because the drift velocity is depending on the crack geometry here. So I will quickly jump to the results. The result is that if you come after the stress is applied, you can show that the probability of the failure of this nano crack is given by this tail. The tail of the probability is sigma squared times tau. Tau is the time you apply the load, okay? So you can see that it gives us a power law tail in stress, power law exponent 2. Okay, then you can calculate from a Fokker-Plonk equation, and that gives you this power law tail. To transit from the nanoscale to the microscopic scale that we proposed this kind of bundle and a chain model, the end result is that if you consider each element is the nanoscale element, then you can show that the strength distribution of one material element will also have a power law tail, but the exponent is power m, is much larger than 2. So now at this point that we want to combine Frantal's idea of a flaw statistics combined with this analysis and see which really governs the power law tail we see on the overall peak load. So the idea is very simple. I will skip this part because the non-local criteria is exactly the same as what we proposed for the MEM structures, but now it's in 3 dimensions. Basically. So again, what we have is the non-local stress equal to strength, and we want to determine where what's the peak load of the specimen. Okay, the peak load of the specimen is reached when any one of the point in the material will satisfy this failure criteria. Okay, so very similar idea, but now it's basically high dimension. Okay, it's not 1D anymore, it's a 2D or 3D. So in the end, again, we can write down the failure probability of a specimen as a level excursion model. But now you can see it's not just the curve. In 2D is the surface, in 3D is really, you know, a 3-dimensional surface. So the question is that if we have a random surface, if I have a barrier lambda, what is the probability that my surface will protrude the barrier? Okay, this is extremely hard question in mathematics. Okay, is a level excursion in high dimension is very hard. The good news is that I only care about the tail distribution. Tail distribution means that my PF is very low, my sigma n is very low, which means my barrier is very high. Actually, this is very advantageous to us. In the beginning, I said that the tail distribution is hard to determine through experiments or through simulations. But from a modeling perspective, tail distribution is easier. Why? Because if the barrier is high enough, you can see the protruding point become far apart. They are more independent. And the shape of the protruding part is more like a sphere-like. And that is really simplified a lot in the analysis. So again, the equation is very similar to the previous one, but now it's in n dimension now. Okay, I can extend this to high dimension. So similar equations, the key thing is to determine the mean crossing rate. In high dimension, mean crossing rate means the average number of protrusion part per unit volume or per unit area. So again, to do this, we have to transform everything to a Gaussian field first. Then, the key point here is that the mean crossing rate is asymptotically approach the expectation of the Euler characteristics. So because in high dimension, we have to go back to differential geometry. And because each protruding part is spherical-like, you can show that actually the mean crossing rate is equal to the expectation of Euler characteristics, which is nothing but invariant of the geometry, differential topology. And I will not go through math here, but you can compute, if you know the statistic of the random field, you can compute the mean crossing rate by this equation, where n is a number of a dimension in analysis. All right, so now we want to put these things together. Now we consider 1D, 2D, and 3D. So 1D case is that you can think about, I have a specimen, okay, a thin specimen, but you have some surface grooves here. So the failure can only happen along this line. The second case is that thin specimen is no surface groove, okay? So the element, the number of element can fail is in this plane where we consider damage is throughout the thickness of the specimen. Okay, or you can think about a bulk specimen where you have, the failure element can be anywhere in the bulk. So we consider stress field. Because of this random, the stochastic analysis of the nano crack, we believe the stress field has to be a Weibul Gaussian distribution with a Weibul tail and with autocorrelation structure here. The stress field, we think that the flaw is, we cannot control the flaw size. So we basically think about all kinds of flaw size. So we consider two types of stress field. One is a power law tail on its right. The second field is a Gaussian with an exponential tail, so totally different tail distribution, okay? Now we're gonna see that if we combine the stress field with the Weibul tail, combined with different stress field, what we get from overall peak load. So in the 1D case, okay, that what you see is that I use the same resistance field, but different stress field 1, stress field 2, plot on the Weibul scale, the statistics of the failure load. The circles you see is a direct Monte Carlo simulation. The solid line is the model that we have. You can see they match the simulation very well. But more importantly, you can see that it doesn't matter what stress field I have. The lower part of the distribution is power law. And the exponent is very close to the Weibul modulus I put in the stress field. The stress field Weibul modulus is 24. So here you can see it's 23.5-ish. Okay? So this tells us that regardless of the stress field I input, actually the overall statistic of the peak load has a power law tail. That power law tail is largely governed by the stress field, but not stress field. So same thing, we can do the 2-dimension. Okay, so there's a random field we generated. I'll just give you a sense of how the random field look like. And then in 2D, 3D, same thing. You can see that doesn't matter the stress field I choose, the tail part is always power law, even though the exponent will change if my number of dimension of analysis change, but not change much. Okay, we are looking at a 22.5 or 22-ish. But on the other hand, I want to emphasize the stress field is important or not. It's important. Of course, you can see if I change the stress field, you can see the distribution function will change. But it does not dictate the power law form of the tail distribution. Okay, that's a key. So of course, you can use a 2-dimensional model, 3-dimensional model to compute the mean size effect. We get something like this. So at the time, we want to know whether this thing is useful, other than understand the power law tail. Then Brad Boyce read our work, and he sent me an email saying that actually at Sandia, they are now interested in this microscale additive manufacture metal. And they also did a size effect, and they show exact kind of size effect like this. Why will be like this? Because in additive manufacturing, there's a lot of flaws in the specimen. There's no control of the flaw size. So it's brittle, and it causes really flaw in the bulk, cause crack initiation damage. So we believe that this kind of level excursion in 3 dimensions could be used to model the size effect we see in this kind of specimens. Okay, so with that, to my conclusion. The 3 main points. First point that we show that the strength distribution of a MEMS device can be represented mathematically by a level excursion model. The key idea is that the failure statistic is equivalent to the first passenger probability. The uniqueness of the model is that it captures the random field of both strength and stress, and also the autocorrelation feature. And because of that, it gives us the complete mean size effect curve. And then I show that the model can be extended to high dimension, okay, 3D, 2-dimension, and 3-dimension. And then we show that the power law tail of strength distribution, this is why Weibul distribution works for brittle structure. Actually, this power law tail can be justified from the stress-driven thermally activated motion of nano crack tip, which is dictated by the transition rate theory. Flaw statistics is important. Okay, it adds more randomness to the overall failure statistics, but it does not dictate the power law tail behavior. The form of the power law tail, the form of the power law tail is not dictated by stress, but by the strength field. Okay, so with that, I will stop here and thank the financial support from ARO and NSF. Okay, so with that, open floor for questions. Thank you.
Thank you very much, Jia Liang, and we are open for questions. We have questions on Zoom. Okay, we'll start with Emmanuel here.
It's a very fascinating lecture. I have a question regarding the first part where you look at this function we call eta naught, which is the difference between the strength and the stress. And you mentioned about this correlation length. And so the example that you gave, if I understood correctly, is that no, you look at these MEMS and then the variation, the fluctuation, the stress field is associated with the geometry of the edge, and then you have another function for the statistics of the strength. But I could imagine also a case where both of them are dictated by the microstructure. So can you comment on that and what does that mean? No?
So from a material science point of view, yes, if you go to the lower scale, you can argue that the material strength, the microstructure can govern both the random stress field and also the stress field. The point here is that this equation, eta 0x, this equation is always true. It does not change. The complication comes is in calculation of this f eta 0, the CDF of eta 0, because these two are no longer independent. And that causes complication in the model. Of course, that the way that we calculate this is everything depends on the property of eta 0. So here, if we assume they are independent, it's easy to compute the PDF of eta 0 and also autocorrelation structure. If you have somehow related, you can do that numerically, but not analytical. So you are correct that, but I think this framework still works, but it's just that you need additional tool to do that.
Randall has questions, please.
Sorry, do you want me to read it? What I'm saying is Gaussian fields have maximum entropy for a specified autocorrelation. This means that in 2 dimensions, for example, your level crossings are independent peaks instead of ridges. This seems like a severe simplification to me. Can you justify the Gaussian assumption that you use in 1, 2, and higher dimensions, other than it makes the problem tractable?
Yes, I heard that, Randall. Yes, so here, of course, that we do not consider that the random field has ridge or sharp ridge. So what we did is that we have a smooth random field and then we transform it to a equivalent Gaussian process. So yes, when you have a ridge, then no. Once you have a ridge, that actually is a mean crossing rate will not be equal to the expectation of Euler characteristics. That analysis will break down.
So the question
and we try to avoid that, again, is through a local averaging of stress field. If you have a local stress field, of course, you will have that. But once you do local average, you actually smooth out the field, basically. Okay. Did he respond? Okay. Oh, okay, sure. Otto? Hi, Otto. Can you ask a question?
I'm muting.
Okay.
Okay, yeah, I have a question similar to Emmanuel's. So could you go back to where you compute the average stresses for your strip? Yeah.
This one?
Yeah. So those singularities, I understand you don't take them into account directly, but they will affect the variation of that sigma bar x, right? So how do you take them into account, and how do you take into account that not only the sigma x will vary, but the shear stresses will be affected as well because of that variation, right? By equilibrium. So what do you do with the shear stresses? Do you consider them, or? And is,
no. Basically here we basically look at the mode 1.
Yeah.
A mode 1 fracture at the notch, V notch tip.
Okay, so yeah, but if the horizontal stress varies, so must the shear stress.
Yes. So in the later 3-dimension case, we do use a principal stress sigma E. That is not it's considered shear stress in 3-dimension case.
Okay, and what I didn't quite understand how you determine that function alpha.
Oh, yeah, it's gonna skip it. The function alpha is basically a weighting function. Typically, that what we use is a bell-shaped curve, and you see in the screen.
Okay. Okay. Well, thank you. Very interesting talk, by the way.
Thank you.
Any questions? I have a question about your potential application. Can you tell more what it is about this additive manufacturing? So you can manufacture this defect in certain way, or?
Yes. What I know is from Sandia is that the additive manufacturing could have just from 3D printing. But when they do 3D printing, depends on printing speed and the printing direction, you have no control of flaws. So the inherited problem in additive manufacturing is that you have a large number of flaws in the bulk. And that causes a significant size effect due to statistics. So the extrapolation will be difficult and the strength distribution will change with the specimen size. So we believe that this model could be used for this. On the other hand, I want to mention that another application of this model we are looking at is that probably you notice that I have to work on a stationary process, a homogeneous process. I cannot go to non-stationary, it will be super difficult. So another thing that we work on is that to use that for stochastic finite element. So a fundamental problem in stochastic finite element is that how can we map a continuous random field of material property onto the finite element mesh? That projection method currently is just averaging or local projection. But for localization instability, we believe that sometimes we need to take a minimum. So how do the minimum in a 2-dimensional random field project to a single point? This level excursion can do the work for us. So that's another application to combine in a stochastic finite element simulations. Yeah, that's a 2.
Manuel?
So you report this amazing experiment by the physicists where they test from 1 millimeter to 1 kilometer. Do you have any idea how they did that? No,
Just a second.
Yeah, I have more story to tell about this work. So this is the picture they put on the paper. Basically, is a wheel that you put. It's a remarkable experiment, I have to say. Yet, they propose a wrong model to explain the data. Actually, we are writing a rebuttal for this. I think the test data is amazing, but they choose a wrong model. And in the paper, actually, that's a point, go back to my first slide, they believe Weibul distribution is empirical. That's what they believe. But this is what they did. That they have an anchor clamp here, as a fiber is somewhere here, and they have just a wheel to pull it to turn the motor, and then they just pull the fiber. When we say that we show them this size effect curve, and they say that they probably could think about how to do the 30-kilometer fiber test. If they can do it, that will be fantastic if we can show this entire curve. But really, let's look at the order of magnitude in the size range. It's, it's enormous size range we are looking at. At the same time, I want to point out that the reason that why we have such a large size range and stop somewhere here is because the randomness in the system is really low, because you have a 5 bundle of filaments. So by central limit theorem, you will expect that the variation of a material property along the fiber is pretty small. That's why you have a huge size range to drop the stress by this amount. If you test this in concrete, I'm pretty sure that in the 4 order magnitude, you will see the Weibul scale, because it depends on how much randomness you have in the model. So it's also material dependent, very much material dependent. Yes.
Okay, I think we exhausted our time, and please join me from home and to thank Jia Liang for an interesting presentation.